Hello, everyone. Hope you all are doing well. I wanted to continue talking about tilings today. Let me know if you can hear me all right, if the music is too loud or too quiet, or if there are any other issues. All right, so I wanted to talk again about tilings, specifically a type of tiling called an aperiodic tiling. So aperiodic tiling. I talked about these in my last stream, but I feel like I did not do a fantastic job explaining the concept, where the idea comes from. So I wanted to take another crack at it and explain the idea, how you might generate these, what you can do with these, all sorts of interesting ideas therein. So let's get started. So let's talk about what exactly is it. What is a tiling, first of all? Usually, with a tiling, you want to tile the plane with some shapes. So I give you some collection of shapes. For example, I could just hand you a square or a rectangle. And then in this case, it's pretty easy to tile the plane with squares. You just you put one square next to another over and over again. On and on and on. And this would be tiling the plane. Of course, this tiling is pretty periodic. There's a pattern here that repeats, right? There's a pretty clear symmetry here. There's a pattern here that repeats. Hello, Alexi. How are you? Nice to see you. So, this particular tiling is periodic. You take a bunch of squares, you just repeat them over and over. That would be an example of a periodic tiling, right? Another example of a periodic tiling you can do of the plane is with hexagons or triangles. So, for example, you could just take hexagons like so. I assume you've seen this before, like a honeycomb, basically. And so on and so forth. So this would be an example, you just extend this out. This would be an example of another extremely periodic tiling of the plane that you can make with this shape, hexagons, okay? So what exactly makes a tiling non-periodic? It's when the same pattern does not repeat on and on forever. Okay. So what exactly is it that makes a tiling non-periodic? So like a classic example that you can give in this case of a non-periodic tiling is, imagine I have right isosceles triangles, right? Like so. Then you can put two together to make a square, right? And then just do that over and over again, right? This would be an example of another periodic tiling. But here's what you do. Just flip one, okay? Like that. But the rest of it, keep it exactly the same, just going up here, it's still in this direction. Up here, it's still this direction, and so on and so forth. You just messed around with one of them. You just messed around with this one right here. But the rest of them are exactly the same. This would be an example of a non-periodic tiling, because as you can see, you messed up the repeating pattern, right? So this is interesting, but not that interesting, right? What I've done here seems a bit trivial. It seems a bit asinine. But this is an example of a non-periodic tiling. Interesting, but like I said, not that interesting. What exactly is it that makes a tiling aperiodic? Well, a tiling is aperiodic if I can tile the plane with it in a non-periodic way, and there's no other way to use the same collection of tiles to tile the plane periodically, okay? That's what makes a tiling aperiodic. So the tiling itself has to be not periodic, and you can't use that same collection of tiles to tile the plane periodically. So of course I've generated some aperiodic tilings. This is the classic one, a very powerful tiling discovered by Penrose. So if you look at this, I'm actually only using two shapes here. I'm using two sets of rhombi, actually. You can ignore the colors. I was just trying to make it look pretty, but it really is, if you stare at it, only two shapes. Here, let me paste a section into Paint and show you that it is only two shapes. Okay. So what makes it so you can see here that let's see, like this is shape 1, 1, 1, 1, 1, and this is shape 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. This is kind of fun. But you get the idea. So there's only like two shapes here, fundamentally. There's like a thin rhombus and like a fat rhombus. And the point of this tiling is that you could not use these shapes. Like if you're forced to use both of them, you could not come up with a way to periodically tile the plane using these shapes, which is kind of surprising. And you can extend this on and on outward forever. The patterns that you see here will never repeat. So let me show that to you very quickly. Let me copy this. Let's do this. Let me just make it a lot bigger. So let's go 16 by 9. And generate the tiling. And of course I'll explain how to make this, how to do this code, how to like do all this stuff, right? So there you go, a much bigger version. And you know, it looks like there's a repeating pattern. There's certainly rotational symmetry in the middle, but as you go outward, you'll notice that the same ideas or like the same concepts are not 100% repeating over here. So can Penrose tiling be symmetrical? No, it can have rotational symmetry. So let me show you the ones on the Wikipedia page. So classic Penrose tiling over here. So you can see that there's a pretty obvious five-fold rotational symmetry to this tiling, right? Like you can rotate this tiling around 5 times and you wind up with the same thing. But as you travel like outward from the center, you'll notice that none of the patterns really repeat. So I hope that's satisfactory here. So these tilings, I mean, it's very interesting that these objects even exist. And very famously, it was believed for a long time that tilings like this could not occur in nature. Like they were just something overly pedantic mathematicians cooked up or something like that. That was the feeling fundamentally, is that tilings like this could not occur in nature. Then of course, actually there's a famous line by like, so the question was, can you find a symmetry, or like, can you find a crystal with this type of symmetry? So as you know, crystals are very important in chemistry. You have to study like the crystalline structure of various objects. And the question was, can you have a crystal with this kind of structure fundamentally? And Linus Pauling, who, as we all know, is an extremely competent and famous chemist, won the Nobel Prize, I think twice, said, no, it can't happen. It's not possible. But he was wrong, of course. Dan Shetman, I think maybe only like 10 years ago or something, won the Nobel Prize for finding a crystal that had this structure, which is kind of amazing. So it's kind of surprising. Maybe not as surprising when you understand like the rules by which. So there are rules you can use to generate tilings like this. In this stream, I'm going to give you a very general and powerful algorithm to create aperiodic tilings yourself. So just to preview the power of what we're going to do. So for example, you'll be able to construct kind of like random aperiodic tilings. So let me just hit enter on this line of code. I should have erased that because it like blasted the previous line of code because I'm using global variables. I know it's very naughty of me, but I'm using global variables. But so if I reset the variables like down here, everything above it gets destroyed. Is this pattern Turing complete? I mean, can we set some initial state and then proceed the tiling? Yeah, absolutely. So I'll explain. I mean, I'm not as sure about something like this, for example. So this is like a kind of a randomly generated one, but I think the answer to your question is yes. And actually, the answer to your question is on the Wikipedia page. For the classical, so I'm not sure about stuff like this. This is just something I made, which I don't know, I kind of like. So you can extend this outward repeatedly on and on forever. But for the classical Penrose tiling, there is a set of rules. So you could use a Turing machine to get it. Let me show you the set of rules that you can use to generate the classical Penrose tiling. Oh yeah, this is it. So this GIF goes, unfortunately, like very quickly, but you can see it. So every time you see a rhombus of the orange kind, you need to replace it with the second frame in the animation, and you just do that over and over again. So it's actually not terribly hard to write down a set of rules to produce kind of like the classical Penrose tiling that you see all the time. Of course, that set of rules that you write down will only create the tiling for will only create that specific tiling. It's not like a general algorithm that you can use to generate all sorts of aperiodic tilings, which is what we're going to focus on today. So the algorithm that I want to talk about it's an extremely powerful and famous idea by De Bruyn. De Bruyn. Also, I don't know why I'm writing in black on like blue paper. Okay. Let me try again. So, this idea here will, De Bruyn's idea will allow us to, I mean, that's what I did in my code, to generate these, and it'll do it like pretty lightning fast and in kind of a lovely way. So, yeah, I'm essentially using De Bruyn's idea. It just takes a couple lines to give you a very general algorithm to generate all sorts of weird and wild aperiodic tilings, which is, I mean, I think that's pretty interesting. So let's take a minute and discuss De Bruyn's idea. So if you wanted something like this, it would be very hard to write down the rules for it. Actually, I can. It's kind of neat. You can use this code to generate random aperiodic tiling. So for example, if you replace if you replace the two initialization vectors, and again, I will explain what all this stuff means in a minute. Right now, for a moment, I just want to like show off and have a little bit of fun. So let's do 10 dimensions. Okay, you're basically like rolling the dice. Okay, so every time you roll the dice, you get like a new wild tiling, which is pretty cool. You can roll the dice again. Ooh, and you can increase or decrease the number of dimensions. So for example, if I drop the dimensions down to 7, it becomes less interesting in a way. You can also change the color scheme. I kind of like the idea of changing the color scheme. Let me choose a fun color scheme. Any input from the audience on the color scheme is also welcome. Here are the options. I'm just scrolling through the color scheme options in Mathematica. Ooh, I like deep sea colors. I'm gonna go deep sea colors. And we can roll the dice again, get a random tiling. Yeah, that's kind of neat. Okay, I should stop moving around. You can also go the other direction and do a very high dimensional one. So this is in 20. This is projecting down from 20 dimensional space. Okay, that's kind of neat. And I kind of wonder what happens if I do 50. Uh-oh. My computer's not happy with me. That's cool. It still has the central rotational symmetry, but these are some pretty wild and pretty fancy aperiodic tilings that we are generating over here. I think it'd be pretty cool to like put this on a wall or like make a wallpaper out of this. There's a way to get rid of the central symmetry that this has. So this is the same if you rotate it 180 degrees. There is a way to get rid of that. I didn't write that in my code. So, but there is a way to get rid of that. Actually, we can just do this. Show plot range. Just do like 0 to 9, 0 to 6. Okay, there you go. So now you're not seeing that rotational symmetry. I just changed where it was like zooming in on, and you can see you get like a very interesting pattern. Make it a little bit bigger. Let's go 20 by 12. Okay, my computer might yell at me for doing this, but all right, it's working. I guess while it's working, I should explain what it is exactly. Okay, yeah, so there you go. I mean, come on, that's really neat, right? It's really kind of insane aperiodic tiling. And by the way, it's with 20 shapes. So it's with, actually, to be honest with you, because I'm randomly generating these, I don't actually know that they're aperiodic, you know? Because I don't know you can't put these tiles together in some way to make a periodic tiling. Like I don't know that for a fact, but it's kind of nifty that there is a way to generate these kind of random tilings. Hello, Prasad. How are you? Okay, so what is it exactly that I'm doing over here? What is this? Well, you'd be surprised. The idea is actually very simple. So it was really shocking to everyone when De Bruyne came up with it and was able to show that it is possible to do this. So let me explain the idea in one dimension, and then we can crank up the number of dimensions as we go. So here's what I'm going to do. I'm just going to start by spelling the word graphics correctly. Okay. So let's plot a line. Let's plot it from the origin to, I don't know, let's go, how about 2, 3? Actually, let's go 20, 30. And we'll do plot range like 0, 5, 0, 5. So I'm just plotting a line. Hopefully. Okay. This doesn't seem too crazy. Whoa, it's a line. I can't believe it. All right. So we have ourselves a very simple line over here, right? Okay. Along with this line, I also want to have a grid, like a lattice grid of where the width and the height of the grid are 1. So I will now do a like table of lines. So let's do table. Let's do a table of lines where my plot range is 5. So we'll do I goes from 0 to 5. Okay. And let's do, so the lines will go from 0i to 5i. What did I do? Oh, I just need to put this in brackets. So the graphics applies to the whole thing. Okay, so once again, nothing too fancy over here. A bunch of horizontal lines. I actually wanted the one on the bottom to show, so I'll go from -1 to 5. Wait, why isn't the bottom line showing? Okay, whatever. So I'm going to do the same thing, but I'm also going to do a set of vertical lines here. So I'll go I0, I5. Okay. I don't really know why the last line is not showing. Huh. Oh well. Okay. We've plotted a line in a grid. You know, nothing too crazy going on here. And now here's what I want you to notice. If you have a line and then you have a lattice like this. Here, let me paste it into Paint so we can examine it thoroughly. Okay, I have my line in my grid, and what I can do is I can try to basically approximate the line with the grid. Okay, so for example, let me move it like over a little bit. Okay, so the line will intersect some vertical segments and some horizontal segments. So if I were trying to approximate this line with only line segments that are on the grid, it would look something like this. You would have first a vertical one, and then this would also be vertical, right? And I don't really know what's going on here. This is a question mark, but this one would also be vertical, right? And then you have a couple horizontal ones as well. So you have this nice little horizontal line, this nice little horizontal line. Again, I don't really know what to do here, but here you have a nice other horizontal line. As you can see, using kind of line segments from the grid, you can approximate any given line. Of course, you need to avoid it going through an actual lattice point. Otherwise, the approximation is not going to work. Okay, hopefully that makes sense. So how can we avoid it going through an actual lattice point? Well, that's easy. I can just make the slope of the line irrational. And because we know an irrational number can't be expressed as a ratio of two integers, guaranteed it will not go through any of these segments here. So if I change my line, right now it goes to 20, 30, but what if I change it to go through 20 root 2, 30? Now you're safe. It will absolutely guaranteed not go through any lattice points, okay? So we just copy this and paste that into, ooh, I don't know why it did a black background, or did a transparent, okay, whatever, I like it. So hopefully this is not too dark. You guys can still see it. Now, notice you can approximate this line by kind of line segments on the grid. So forget about the origin. You have vertical, 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 and then you also have horizontal. So you have this horizontal, 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 horizontal. Okay? But here's the thing. Because the slope of this line is irrational, no pattern that you're seeing here could actually repeat forever, right? If it did, then the slope of the line would actually be rational instead of irrational. Okay? So interestingly, if I look at my sequence of alternating, like vertical horizontals, right? If I look at this sequence of vertical and horizontal, if the line has an irrational slope, it's not going to repeat forever. So let me see if I can demonstrate this. So let's increase the plot range. Let me set a parameter here. Let's do width n equals 10. We're showing a graphic. Let's multiply this by n. Okay, and then this goes to n. This goes to n. This goes to n. This goes up to n. This goes up to n. Just need to close the parentheses. Oh, I forgot to, okay, this should have been an n. Okay, perfect. Let's, actually, let's make it even bigger. Let's make n like, I don't know, 50. Okay, this is not supposed to go through any lattice points, but it like looks like it is, but I swear it is not, because this line is supposed to have a rational slope. I just need to like zoom in a lot. Okay, so now you can see the pattern here. You can, now I mean this is just a thank you Petros, but I don't know. I'm just messing around and trying to do a quick demonstration over here. But I want you to look at this. If you zoom in really hard, right? you notice this goes horizontal, vertical, horizontal, vertical, horizontal, vertical, horizontal, vertical, horizontal, vertical, horizontal, vertical, horizontal, vertical. It does that for a while, right? But then notice the pattern will shift over here. So it's vertical, horizontal, vertical, horizontal. And now notice the pattern changes direction. You see that? So this pattern here, it just, because the slope is irrational, this pattern of verticals and horizontals that you're seeing here, it cannot repeat forever, okay? And so this is the idea we're going to try and take advantage of in order to get our aperiodic tiling. So you can imagine if you have a picture like this, what you can do is you can project all of these, you can kind of project this approximate line back down onto the line. So just imagine squishing this approximate line back down onto the line. So if you squish this back down, you know, this yellow would become like this. This orange would become like this, right? This yellow would become like this. You know, I'm just squishing it back down. So this yellow would be like this. This yellow would be like this. Yellow would be like this. This orange would be like this. This orange would be like this. This orange would be like this. Okay? And so in doing so, I have now tiled my line with line segments. The same line segments over and over again. It's just a set of 2 line segments repeated, right? However, this will be a non-periodic tiling of this line. Does that make sense? So it could not alternate forever. If it alternated forever, the slope of this line would be 1, right? So at some point, the pattern has to shift because the slope of this line is, you know, I think it's like √2/3 or something like that. So I know this pattern will stop and change because the slope of this line is irrational. And so this is essentially the idea that we're going to be using in order to generate these crazy tilings of the plane. So instead of using a line, what if I instead used a plane, right? Like what if I had a plane? And now imagine that all of Euclidean space is divided up into cubes, you know, like a cubic grid, okay? Now you try to approximate this plane using the cubic grid. What's going to happen, right? Right, you can do your best to kind of approximate this plane with faces of a cube that appear on a grid, and you will get some wild and crazy pattern if you picked the right plane. If you picked the wrong plane, you'll get a very kind of like regular seeming pattern. So let's see if I can't show you the actual, hold on a second. So I'll have to modify my code a little bit, but I just came up with an idea to illustrate exactly what it is that I'm talking about to you guys. So let's see here. I'm going to create a new function. We'll call it frame2. This will only work with 3D vectors, so I just need to be careful. So okay, I need a new version of this function too. I'll call it romby2. You get to see me be a terrible programmer live. So, all right. So here's what I'm going to do. I'm not going to project. So this last line, the projected squares, is the line of code that squishes things back down onto the line. So it squishes the like this pattern back down onto the line, right? And so I'm just going to get rid of that first and foremost. So I'm just going to delete that line and just return the hypercube centers and close that bracket. Okay, so let's see here. Okay, it'd be lovely if this just works. All right, Let's see what happens. So this code. Okay, I also need to change this to a 3D object. All right, it's gonna be a miracle if this works. Let's see. So frame 2. Let's do 2 random real vectors. 1, 3. Okay, and let's go 9, 6. Okay, error. Hold on, let me, let me just, print the lattice squares and also return them. All right, I just want to print out of the. Okay, no, this is looking very good. Oh, whoa! Why is this working all of a sudden? Okay, I don't really know why it's working all of a sudden, but there you go. That's actually a really good picture. You can see now. Wait, I don't know why it wasn't working before, but you can see now how there's just like a plane, an underlying plane, with a weird irrational slope that's basically being approximated by a cubic grid. Okay, let me know if that makes sense. So there's like a flat plane here, and you're doing your best to approximate it with a cubic lattice, which pretty much exactly what we were doing with this much simpler picture inside R2. So let me know if there are any questions about that. I actually think this picture illustrates it pretty well. So you can see that there was like a plane somewhere, right? And if you pick the right plane that has the right irrational slopes, you'll kind of get non-repeating patterns on the plane. I don't know why it didn't work the first time though. See if it yells at me again. Okay, now it's a different plane being approximated. You can see it, right? You can see the plane that's being approximated by the lattice cubes. Now all you need to do is you need to squish or project these squares back down onto the plane, and you have an interesting tiling of the plane. So if we change this frame 2 back to our original frame, you can see it's a flattened picture, but now it just, okay, so now you know where this picture is coming from, okay? So does that make sense? Are there any questions about this? So you're just taking a plane inside R3 and you're trying to approximate it with cubes, and then you flatten it down. You just project it down back onto the plane, and you can see the actual plane here. I have a massive like numeric printout, but like here it is actually attempting to approximate the plane. But because the plane has like weird irrational slopes, right? You can see there's kind of like a non-repeating pattern going on here. Okay? So if that makes sense, and I hope it does, I hope it's clear how you would extend this further and further. So I just did this in R3, and this is what it came to. But you can do this in any Rn, right? It's just numbers at the end of the day. The computer just has to kind of approximate the plane with squares on hypercubes, right? And just project them back down onto the plane, right? It's, you know, it's no more... I know it's hard to like wrap your head around like higher dimensional stuff, but like the algebra is no more complicated in some way. It's no more, can you show the code line where you squeeze it? Oh, so, okay, so this is the code line where I squeeze it, but it's not, that's not, no. Projecting it from higher dimensions is actually very, very easy. So watch. So that's actually not the hardest part. I'll explain what the most annoying part is. But if you've taken your like a calculus or a linear algebra class, there's this really neat thing called a projection formula. You learn this when you take like you learn this in like linear algebra, or if you've taken like multivariable calculus, you learn this as well. So let's say you have two vectors like v and w, right? And you want to come up with so look at the line kind of spanned by w. So this is the line spanned by w. You want to come up with the vector on the line spanned by w that's closest to v. So you're basically interested in this one. So I'm kind of squishing v onto w, and the way you do that is so this is the projection. I'm going to call it like u or something. You're interested in what this vector u is, and there's a really neat formula. It comes down to the fact that this has to be a right angle if you're projecting down effectively, right? So u will have to be v dotted with w over w dotted with w times w. Very simple little formula to squish down. And so that's fundamentally all you need to kind of squish this picture down to, so that formula is literally it. That formula is all you need to squish this picture down to, let me stop printing all of this debugging code. Okay, so if you're interested in just projecting this onto an actual plane, that's all it is. I mean, I just shared it with you. That's all the math you have to do. So, okay, how do you project? Okay, so I showed you how to project down to a line. How do you project down to a plane? Well, it turns out that if you're careful, let's say you take a plane that's spanned by two vectors. Let's say the plane is spanned by w1 and w2, right? If the plane is spanned by two vectors, so it's the plane created by these two vectors, right? The plane kind of spanned by these two vectors, and you're projecting v down to this plane, as long as w1 and w2, so the two planes spanning the vector, are at right angles to each other, the projection of v down to this plane will just be the sum of its projections down to w1 and its projection down to w2. So really simple algebra here. So does that answer the question of how you project v down onto a plane? So this is your plane. This is your vector v that you want to project down, and then what you do is you take two vectors that are at a right angle to each other that span the plane. So this is, let's say, w1, and let's say this is w2. These are at right angles to each other. All you need to do is project v down to w1 using this formula, v down to w2 using this formula, add the two, and you will have squished v onto the plane. Okay, so if w1 and w2 are at right angles to each other, then this u is just going to be like v dot w1 over w1 dot w1 plus v dot w2 over w2 dot w2 w2, and that's it. That's the formula. I realize I'm like writing over myself, so hopefully that makes reasonable sense. Okay, that is how you do the projection. So what is actually the annoying part of this? What's actually kind of hard to do? The annoying part of this, the part that's like a little hard to do, is actually just coming up with the squares, right? Like which squares. Okay, so there's like a two-step process here. I need to kind of like isolate the region of the plane that I want to make a picture out of, right? So you can imagine, this is my plane sitting in space, right? I need to like pick the section of the plane that I'm actually going to show you, right? That's actually going to be plotted, right? And let's see. Yes, thanks. The difficulty was imagining hypercube tiled 4D space and plane cutting through it. I mean, no one, I don't know. I mean, you can kind of imagine it, but I guess the point is hopefully don't imagine it. Just trust the algebra, right? I mean, I don't want to like, I guess on some level, I hope you accept that you can tile 4D space with hypercubes and 5D space with like 5-dimensional cubes and 6D space with 6-dimensional cubes. And you can do the same thing. You can basically like apply this process no matter what. So the hard part algebraically, anyway, I would say it's not that hard, but like the annoying part algebraically is just, okay, so this is my plane. I need to like figure out what cutout I'm going to take. And then, you know, you have to figure out what squares are going to kind of like approximate this effectively. That's a little bit tricky. That's a little bit tricky. So here's how I did it. This isn't my idea. Once again, this all comes down to De Bruin. I don't know how to say his name, but you can. I've included links as well in the description. I hope I didn't forget to do it. So you can click on those to see other people's ideas and implementations as well. And okay, what is the hard part? Well, let's go back to the line. It's a little bit harder when you have a plane in n-dimensional space and you want to figure out what, like, right? You're trying to figure out what faces of the hypercube the plane is kind of like cutting through. That might seem like a very annoying algebra problem, right? Here's how to get around the annoying algebra problem. Okay. So here's like the bad way to do it. Okay, you look at all the hypercubes and you actually enumerate all the hypercubes, and then you see all the faces that the plane is going to cut through. That's bad because you need to loop through everything over and it's a nightmare, right? It's an absolute disaster if you do that. Okay, so here's the idea. Let's go back to the line so I can explain the idea, and then you can see how it's extended out further and further. So here's what we're gonna do. You have your line. You know, it goes through your grid. Hold on. So Penrose says, when you have two kinds of tiles, this means that the line. Yeah. So the two different lengths just come from vertical and horizontal. So what's going on here? So this is the actual. I don't think it's exactly, but this is basically like the Penrose tiling, right? What makes this only have two types of. So in the Penrose tiling, you're projecting down from 5-dimensional space to a plane. That's how you get it. The reason this only has like two tiles, so if you're projecting down from 5-dimensional space, well, let's think about how many faces a cube has in 5-dimensional space. So a square has just 4 faces, right? 4 like facets, right? So it only has like 4 outermost things, and for a cube, it's going to be 1, 2, 3, 4, 5, 6, right? You have 6 faces. And so on and on it goes. So like as you go into higher dimensions, you wind up with more and more. Well, actually, I should be careful. You're only enumerating 2-dimensional faces of a high dimensional cube. But in any case, the numbers should keep going higher and higher. But the reason there's this interesting symmetry is that you choose a plane where different versions of the face projected wind up being different versions of each other. So if this is a little bit hard to see, let me do this with just 3 dimensions. Okay. So this is in 3 dimensions, but I chose the plane that's orthogonal to 1, 1, 1, right? And so you can see all the different faces of the cube here, right? But they're actually all isomorphic to one another, right? They're all congruent to one another, right? They're all rotated versions of each other because I just chose my plane in a way so that they're all essentially the same. Does that make sense? And so when you look at the Penrose tiling, or this isn't, like I said, this isn't quite the Penrose tiling, but my like weird version of it. You know, these are all, you can tell by the colors which are supposed to be the same like two-dimensional faces of the higher dimensional cube. So things that are the same color came from the same space. It came from the same face, the same type of face of the hypercube. So you can count that there are more faces here, but a lot of them wind up being congruent to one another. So you look at all of these in the center here. These are all just rotated versions of each other. Okay. All right. So Petra says he gets it. Let's keep at it. So, all right. How do you get out of the like annoying algebra problem that we have set up for ourselves here? So here's a solution. Once again, this is not my solution, but here's a great solution. Here's what you do. On this line, I want you to just pay attention to the points that have either an x coordinate, an integer plus a half, or a y coordinate that's an integer plus a half. Okay? So you just mark all the points that are like right in the center of a square, either in the x direction or at the center of the square in the y direction. Okay? So maybe this point is at the center in the y direction, and you know, hold on, let me make it a bit more exaggerated so that it's clear. So let's say this is the line, right? And let's draw the grid real quick. Okay, it should not be going dead through one thing. Okay, this is my line, this is my grid. Okay, so now this point looks like it's at the center in the y direction. This point kind of looks like it's at the center in the x direction. This point kind of looks like it's in the center in the y direction. This point looks like it's in the center in the x direction. Hopefully that makes sense. So you essentially solve for all the points where either the x coordinate or the y coordinate are an integer plus a half. And what that means is that point is at the center in the x direction or at the center in the y direction. Okay? So let's think about what this means exactly. So this is like a snippet of your line. So like this is the square, right? And let's say you have your line going through, maybe like so, right? And you say to yourself, okay, I do not want to change the color of that line. Hold on. And then you realize that, okay, wait up. This point is in the center of the square in the y direction, but not in the x direction, right? Notice that tells you exactly what face of this square you should be using. See, if you're in the center in the y direction, in order to solve for this closest face, here's what you have to do. If you're in the center in the y direction, add a half to this, you get this point. Subtract a half from this, you get this point. And whatever the other coordinate is, round it, right? Whatever the x coordinate is. So maybe the x coordinate of this point is like 5.236 or whatever. Round it. If you round it down, you'll get 5. And now notice when you do that, you will get exactly these 2 points. So hopefully that algorithm is clear. So let's say so this point is in the center of some square in the y direction, and it has some random x coordinates. So let's say that this point that we've found over here has, let's say its x coordinate is like 5.236, and let's say its y coordinate is 2.5. Okay, hopefully that makes sense. Then what are the coordinates of these 2 points going to be? Well, it's going to be 2.5 plus a half, 2.5 minus a half, so 3, 2. And then whatever remain is, you round it down. So this is 5.3, and this is 5.2. And now that you have 5, 3, and 5, 2, you have the exact line that you need. So you just do this over and over again, and it will perfectly like give you your approximation of your line. So you just take your line, right? Solve for all of the points where the x coordinate or the y coordinate are an integer plus a half, like so. And whenever you're given such a point, let's say the y coordinate is an integer plus a half, you can add a half, subtract a half, round the other coordinate. That will give you very quickly the line that you need. Okay? And that's it. That's essentially the algorithm. Okay, so how do you use it for a plane in like n dimensions or whatever? Let's start with 3 dimensions first. So this is my plane. All you need to do is mark all the points where 2 out of the 3 coordinates. Okay? Thank you for some. All you need to do is mark all the points where 2 out of the 3 coordinates are an integer plus a half. So you just mark all of these. So, you know, 2 out of the 3 coordinates are an integer plus a half. You mark all of those points. Okay? Okay, so let's say in this point, remember, it's 2 out of the 3 coordinates are an integer plus a half. So let's say this point, if we zoom in on it, let me write over here. This point, if we zoom in on it, let's say it's like a half, 2.5, 3.7. That's what this point is, let's say. Okay, so how do I get a hold of this square? Oh, that's easy. From a half, I add and subtract a half, and from 2.5, I add and subtract a half, and 3.7, I just round. So what are the 4 coordinates of the square that are closest to this point? Well, that's easy. It's just 1, 3, 3, 0, 3, 3, 1, 2, 3, and 0, 2, 3. Those are the 4 coordinates of the square that's closest to this particular point. If you're having trouble seeing that, just imagine this point sitting at the inside a cube, right? I can't draw to save my life, but okay. This point is in the middle in the x direction. It's in the middle in the y direction. But it's very close to the top in the z direction. So maybe this point is like up here or something, right? So because it's in the middle in the x direction, I can just add and subtract a half in the x direction, add and subtract a half in the y direction, and just round in the z direction, and that will give me these 4 points. Done. Okay? So now, for an n-dimensional plane, remember, an n-dimensional plane is just the span of 2 n-dimensional vectors, right? So if you have a 2-dimensional plane sitting in n-dimensional space, remember, every plane in any dimension is just all linear combinations of 2 vectors. You just take 2 vectors, independent vectors, and you take all possible linear combinations of them, you get a plane, right? So you take 2 vectors and you take all possible linear combinations of them, assuming they're independent, you should get a plane. So all you need to do is pay attention to those linear combinations where 2 of the coordinates are an integer plus a half, but the remaining coordinates can be whatever. And then you just do this procedure that I've outlined. I mean, even if it's 100 coordinates, it's not too bad, right? So 2 of the coordinates are going to be an integer plus a half. The rest are going to be whatever. So just for the 2 coordinates that are an integer plus a half, just add a half, subtract a half, add a half, subtract a half, round the rest, and that will give you the quadrilateral, or like I guess it's literally a square that's closest. And then all you need to do from here is just project it down onto the plane. And that's it, really. So yeah, I don't even know what else to say. One cool thing you can do is you can interpolate between random vectors, which is a lot of fun to do. So you can start with the Penrose tiling, and then you can kind of 1-parameter family it to a random plane. So this is what that looks like. So this is what it looks like. If the plane moves, the tiling will change. Isn't that neat? So I'm moving the plane in a 5-dimensional space, and you can see the tiling move as I move the plane. Come on, tell me that isn't cool. Woo. Going back to the Penrose tiling. I can re-roll. So basically I'm interpolating between like the plane that gives me the tiling that looks like the Penrose tiling and then a random plane in R5. I can re-roll and get a different random plane in R5. Let's see what this looks like. But it's kind of relaxing watching a plane move around in R5, isn't it? And once you know what it is, I have to say, your brain is able to like wrap your head around like, oh yeah, this is like a plane moving around. I kind of see it. Let me know how you guys feel about this. I think it's very beautiful. So this is just like a random plane moving around. And of course, in R5, oh god, the music got intense. Hold on, I need to skip the song. All right, maybe I'll louden it just a tad. Okay, so, you know, in R5, there's just, in R5, the computer is able to do the computations quickly enough where you can do these like animations and it will compute the animations in real time. Of course, I haven't written this code for like efficiency. I just wrote it to have fun. But if we move the dimensions higher, going to like R7. So this is in R7. So this is now like a Penrose style plane in 7-dimensional space projected down, and then you can move it around. So then now this is a plane moving around in 7-dimensional space. That's very nice. And I love stuff like this. Thank you, everyone. Yeah. And yeah, you can just have fun. So let's see here. Let's do let's see. Let's do the Penrose plane. A bit of magic disappears after you are getting what's happening under the hood. That is, well, okay. That is true, but once you know what's happening under the hood, well, I guess knowing what's happening under the hood is what allows you to make the magic in the first place. So if you know what's happening under the hood, then you can hopefully make more magic. So let's see if we can't come up with something else that has a little bit of magic to it. So let's see here. What I'm gonna do is I'm gonna get rid of the manipulate. Just take this away. I'm kind of curious what it looks like if I do the Penrose one in a really high dimensional space. So this was 7, right? But I don't know. I'm kind of curious what happens if I do like 30 dimensions, right? So let's see what happens there. And I might pick a different color scheme. I feel like I'm getting sick of the ocean. So I'll let you guys pick if you see any like color scheme that you like. Okay, I can't really zoom in on this, but I guess I'll just pick one. Okay, how about this? Be such a flex to tell your. I know, right? And it's yeah. I mean, also let me know if any of you want the code. I don't really can release it. Okay, I'm gonna go green pink tones. Yeah. Magic pours right in when you understand the moment when the plane gets perpendicular to some base and the pattern changes rapidly. Yeah, I know, right? Okay. Let's try an R30. You guys ready? This could be fun. Okay, my computer's chugging now. It is cooking. I really need to start programming in other languages again. I've gotten so rusty with like Python and stuff, but I've also just become so fast with Mathematica that it's like really hard to do anything else. Also, I have a feeling this is gonna crash. Oh, cool. What do you know? So this is now projecting in R30. So this is in 30 dimensions projecting down onto a plane. That's really beautiful, I think. I think that's really nice. So, I don't know. Hopefully some of the magic has returned for everyone. I actually think that's really beautiful. And I can hear my computer's fans slowing down. I'm open to ideas, by the way. So, okay, here's one really naughty thing that I did, and I'm sorry about this. To get the true Penrose tiling, your plane has to not be going through the origin. And I kind of forgot to do that in my code. So all of my planes are going through the origin. Maybe if you implement this yourself. I mean, it'd be really annoying and difficult for me to do it now because I've already like done everything. But if you're doing this yourself, just make sure you have like a shift parameter that'll put the plane away from the origin, and then you can get the same tiling that's on Wikipedia. So I'm kind of curious what just a random one would look like in R30. Yeah, it's really sad because I think you could get other really amazing kind of symmetric patterns by just, so like that plane was, I mean, so that tiling was really beautiful, right? What if we just shifted the plane? So it maintained its symmetries, but what if we shifted the plane by like 1 unit orthogonally away from the origin? I feel like that would give you something really beautiful as well. But sadly, I forgot to write that in when I was writing it out. So all of you fine folks, feel free to do it. I know I've already done this, but I love just doing random ones. So let's see here. I know I've already shown you some of these before, but I'm going to show you some more because I feel like it. Also, if any of you have ideas on what to do, I'm open to it as well. If you want to see this again with the like shifts, I can code that in as well. I think it would take me like 30 minutes to figure out everything. So I'm not going to do that live. Just kind of curious. Okay, yeah, so this is a random one in R50. So that's kind of neat. I know I showed you guys these already, so that's pretty cool. So yeah, this is a random tiling that's probably aperiodic. But yeah, imagine tiling your imagine tiling your wall or your bathroom floor like that. I think that'd be a lot of fun. All right, I think that's basically it for me. I've said everything I've wanted to say. I've shown you everything that I've coded. It's kind of neat. I am disappointed that I forgot to include a shift parameter that shifted the plane away from the origin, but I will leave that to you guys. I've had a lot of fun. Would love to see spherical cut through projection in 3D space versus projection onto spherical surface. Huh. I'm not sure it's that much work, actually. I think I could do it, but probably not on stream. So you might have to catch me some other time to do that. But that's actually not that bad. There's like inbuilt stuff for Mathematica. So hold on. Alexi says, interesting to optimize a pattern to match some arbitrary image, although it might. That's actually, I think, really hard. Hold on, let me think about that. I'm not even sure how I would do that. Wow, that's a really great idea, Alexi. You should totally get to work on that. Can you imagine, like, if you could come up with a tiling with like someone's face in it or something like that, you know? I think that'd be really cool. I think that's a beautiful idea. I have no idea how to do it, but I think that's a very beautiful idea. Oh man, like you'd have to be projecting down from like R1 million or something to get it to look right. Now I'm thinking now the wheels are turning. How would you do that? I'd have to think a lot about it. Like, that's a very hard. I think that's actually a very, very, very hard problem. But I'm gonna stop talking now. I hope you guys have enjoyed the stream. I had a lot of fun with this one. I had a lot of fun with this one. I was able to make some beautiful things. Maybe I'll do like one more in the Penrose style, but zoomed in at a different like angle. Let's do 50 again. Okay, this will make my computer be very unhappy, but I think. Okay, I have nothing else open, so it'll probably take a minute for it to compute this image. Let's see what it looks like. All right. In the meantime, I will continue to think about Alexi's idea. I got nothing, man. That's hard. Hold on, it might not even make it. I might have to end the stream without. I'll give it another minute for it to like try and finish this computation. So I'm doing like a Penrose style tiling in R50, but I also set the like plot range to be massive as well. So let's see here. And then I'll leave you guys alone. Yeah, it might not make it through. I should have set up some kind of like progress bar or something. Well, I don't know what to talk about while we wait for my computer to do this. Yeah, I really wanted to show up. I think it'd be a good thing to end the stream on, but it might be too hard for my computer. We're still waiting. I think I may have asked for too much. Okay, guys, I'm sorry to disappoint, but I don't think this is happening. Yeah, I don't think this is happening. So thank you so much to everyone that showed up. It was a real pleasure. I really had a great time working on this. And I will see you all again on Wednesday at 1 p.m. In the meantime, I hope you guys have a lovely, lovely weekend. Peace.